Alright, so today's just going to be a quick video. I want to go over this power supply right here. It's a high voltage power supply. I'll be using it in a Tesla coils that I'm building. I'll get into that in a different video. Today we'll just focus on well, measuring, because that's actually part of why I'm making this video. So once I know the output values for this transformer, I will be able to set up and configure my MMC, so I know, how many capacitors do I need, what value on them, and so on and so on. So today's video, well, it's basically gonna be, I'll go over inside, like how it's built, what the setup is, we'll do the measurements, and in the end maybe we'll draw some arcs, just for the heck of it. So let's go. So what do we got on the inside? Well, it's a pretty typical dual-MOT setup. You have the two transformers, and up here you have the ballast. Usually you would use a MOT for a ballast. You just hook it up to the primary, the secondary is shorted out. I'm not a huge fan of that setup, honestly, because MOTs are pretty unreliable, and if you overload them, they like to catch on fire, and the secondary might melt. So for something that's going to be used continuously, I wouldn't do that. That's why I made my own ballast. It's made out of a basically MOT core with windings that I put on the central leg. The power comes in here, and the neutral then connects directly to the primaries on the MOTs. Live wire goes to this connector, and this here is what then goes to the ballast. That thing can be then connected in series with the windings on these transformers, or it can be completely bypassed if you want to have more power on the output. The high voltage side is pretty simple. You have the center tap of the transformers right here, just a jumper wire going across the frames, and then from the high voltage lugs right here, you have two wires going to the output terminals. Now, the output terminals are just low voltage insulators that I used as a bushing because, well, they do have a hole completely through them. And on the back, if you can see, there are just these plastic washers, basically. The wood should be enough to insulate against the voltages used here, but just as a safety measure, I just made sure that the bolt doesn't actually touch the wood. So that's all I can really say, I guess, about the interior of this thing. So let's get on and start doing the measurements, see what kind of values we have on the output there. Now, to measure the output voltage, we'll be using this multimeter right here. It goes up to 5,000 volts, so we should be fine on that. Now, this is not my multimeter, so I have to remember to actually return it later. But let's hook it up to the output and see what voltage we get. We're gonna measure both with the ballast connected and disconnected. Okay, so it is hooked up right now. Let me zoom in a little bit on the display here so you can see what's going on. Now, this is with the ballast disconnected, so we will be measuring the unballasted output, which should be a higher voltage. And as you see, we are getting just under 4,000 volts. Okay, so the ballast is now connected, and now that I plug it in, I should be getting a lower voltage on the output. And as you see, we are indeed getting, well, just under 3,000 volts. So with the ballast connected, you're basically getting 75% of the full power. So now that we know the voltages, we can go and measure the current draw on the primary side, and we have both unballasted and ballasted with and without load. Okay, so first of all, we're going to measure the current without the ballast and without any load. So let's plug it in, and we are getting about 4.89 amps. Well, 4.9 basically. Now we're gonna test it under load. I'm basically gonna draw an arc across the output and see how much current it's gonna take. It looks like we're going to about 20 amps. So that's gonna be my estimate. The power meter doesn't go beyond 20 amps because it just gives an overload screen. But 20 amps and probably more if you keep it running, but... Okay, I've connected the ballast without any load. Let's see how much we get. Without the load we get about 0.74 amps. So, as you see, the ballast is actually doing a pretty good job at limiting how much current this thing draws. Now, let's short it out. And we get about 3 amps. This is a continuous short across the secondary, basically. So 3 amps on the primary at full load, that's not too bad. We can then use the ratio of the transformer and convert that into the current on the secondary, and that lets us then know how many strings of capacitors we will need for our MMC to be able to handle this current throughput. And now let's get to the fun part. Let's see how the ballast affects the size of the arc. I've put a centimeter scale on the backdrop there, so it goes in increments of 5 centimeters. So it have, 5, 10, 15, 20, 25, and 30. This is with the ballast connected, and the arc is actually really measly, as you see. It's pretty hard to even keep it going. So let's remove it and see how the arcs will look. So you see it gets it to about 20 centimeters in height. That's obviously not enough, so we need a little more. We can actually plug in capacitors on the secondary side right here, and that's gonna drive the voltage a little bit up, so we're gonna have an even bigger arc. Let's do that. Alright, now we have 2 capacitors plugged in on the secondary side, and this is probably gonna be pretty bright. It's actually going past the scale that I have, so it's about 40 centimeter arcs. Well, I don't really think I have anything else to add about this, so I'll just say that, as it always goes with high voltage, be careful, know what you're getting yourself into. And other than that, thanks for watching, and I'll see you in another video.